Guide the flow to the center.
Steady, keep it steady now.
All right, easy, easy. Looks good. This section is reading 45 millimeters.
Within specs, the forging is sound.
We must press the attack on Convoy 47. The timing is critical.
But Admiral, the escorts are stronger than anticipated.
Dive! Flood the tanks!
Bridge is clear. Hatches secure, sir.
January 1942. Before sunrise, the air inside Bethlehem Steel's Pennsylvania works is already heavy with heat. Furnaces glow white. Overhead, cranes move like slow, deliberate animals. Molten steel pours into molds, throwing sparks against concrete walls stained by decades of industry. Outside these walls, America is at war. In the Atlantic, German U-boats are sinking merchant ships within sight of the coastline. In the Pacific, submarines are being ordered faster than they can be delivered. On paper, the United States Navy has designs, crews, and urgency. What it does not have is steel that can survive the ocean's pressure. Submarines are different. They do not fight the enemy alone. They fight the sea itself. Every dive compresses the hull. Every ascent tests invisible fractures. A single flaw, too small to see, too deep to detect, can turn steel into a coffin hundreds of feet below the surface. By early 1942, the Navy knows the truth. America cannot build enough submarines because it cannot forge the steel they require. And somewhere between these furnaces and the dark water beyond the horizon, that realization begins to change everything.
The strategic problem beneath the waves, ***. In the years before the United States entered the Second World War, submarines occupied an uneasy position in naval thinking. They were recognized as useful, capable of reconnaissance, harassment, and commerce raiding, but they were not yet considered decisive instruments of strategy. Battleships still dominated doctrine. Aircraft carriers were only beginning to redefine naval power. Submarines, by contrast, were constrained by range, endurance, and above all, by how deep they could safely dive. Depth was survival. By 1939, Germany understood this with ruthless clarity. Admiral Karl Donitz had built his U-boat arm around one central idea. The ocean itself was the submarine's primary weapon. German boats did not need to outgun surface escorts. They needed to disappear beneath them. Every additional meter of depth increased the chance of evasion. Every reliable dive below a destroyer's effective depth charge setting turned steel into invisibility. German industry had been preparing for this long before the war began. Krupp and other firms had refined pressure hull metallurgy through years of experimentation. German submarines used thick, high-tensile steel cylinders, forged and welded under tightly controlled conditions. The hulls were designed to flex slightly under pressure rather than crack. It was an expensive process, slow and technically demanding, but it worked. By 1940, U-boats were diving deeper than many Allied escorts could reliably attack. The United States Navy watched these developments closely, but from a distance. American submarines were built to different assumptions. The Pacific, not the Atlantic, was their expected battlefield. Wide, open spaces where endurance mattered more than extreme depth. Pre-war U.S. designs emphasized range, habitability, and surface speed. Dive depth, while important, was not pushed to the limits of metallurgy. That distinction would matter. When war came in December 1941, it arrived faster than industrial reality could adjust. Submarines suddenly moved from a supporting role to a frontline necessity. In the Atlantic, German U-boats were sinking Allied shipping at a rate that threatened Britain's survival. In the Pacific, the U.S. Navy needed submarines capable of penetrating Japanese-controlled waters, operating for weeks at a time, and surviving increasingly effective anti-submarine patrols. The Navy's answer was simple in theory: build more submarines, faster, and make them stronger. In practice, the problem lay inside the steel itself. A submarine's pressure hull is not ordinary ship steel. It must endure repeated cycles of compression and release. At depth, every square inch of hull bears thousands of pounds of force. Microfractures, imperceptible at the surface, can propagate catastrophically under pressure. A weld that holds during inspection can fail after dozens of dives. Steel that performs perfectly in a battleship's frame can shatter when shaped into a cylinder and pushed beyond its elastic limit. American steelmakers knew how to produce armor plate. They knew how to roll structural beams. They even knew how to forge large naval components. What they had never done at scale was produce long, thick, defect-free pressure hull sections designed to flex rather than resist. By early 1942, Navy inspectors were rejecting submarine hull sections at an alarming rate. Ultrasonic testing was primitive. X-ray inspection was limited. Many flaws were only discovered after destructive testing, or worse, during deep dive trials. The result was a quiet bottleneck. Designs existed. Shipyards were expanding. Crews were training. But the steel, heavy, precise, unforgiving steel, was holding the entire system hostage. And that reality forced the Navy to turn not to admirals or shipbuilders, but to the heart of American industry, where one company stood at the center of the problem: Bethlehem Steel. Bethlehem Steel and the limits of pre-war industry, ***. By the time America entered the war, Bethlehem Steel was already a giant. Its mills stretched across Pennsylvania, Maryland, and beyond. Its steel framed skyscrapers, railroads, and bridges. Its armor plate protected battleships and cruisers. In peacetime and war alike, Bethlehem had been synonymous with industrial reliability. But submarines demanded something Bethlehem had never been asked to provide. Traditional naval steelmaking focused on strength through mass. Thick plate, rigid structures, armor that resisted penetration. Submarine pressure hulls required the opposite philosophy. They had to be strong, yes, but also predictable. The steel could not be brittle. It could not hide internal weaknesses. It had to deform slightly under pressure and return to shape again and again without accumulating damage. That behavior depended on grain structure. Inside every forged steel component, microscopic grains form as the metal cools. If those grains are uneven, elongated, or interrupted by inclusions, the steel will behave unpredictably under stress. Pre-war forging methods often produced acceptable results for surface ships, where stresses were distributed differently. In submarines, those same internal irregularities became fatal liabilities. Bethlehem's existing forging presses were not designed for the dimensions the Navy now required. Pressure hull sections had to be large, thick, and uniform. Welding together smaller pieces increased the number of seams, each one a potential failure point. Yet forging single-piece sections of that size pushed equipment beyond its intended limits. When Bethlehem attempted to adapt, problems surfaced almost immediately. Some forgings cooled too quickly at the edges and too slowly at the core, creating residual stresses locked inside the metal. Others developed non-metallic inclusions, tiny impurities trapped during pouring or forging that acted as crack initiators under pressure. Surface inspections passed. Mechanical tests looked promising, but when subjected to simulated depth loads, samples failed without warning. Navy inspectors were relentless. They had to be. A submarine hull failure was not a irreparable accident. It was a total loss, measured not only in steel and machinery, but in lives. Reports returned to Washington describing steel that met written specifications yet failed operational reality. The specifications themselves became suspect. Before the war, American standards had been shaped by availability and experience, not by deep ocean physics. Yield strength, tensile strength, and elongation were measured in isolation. What they did not fully capture was fatigue under cyclic pressure. A hull did not fail in one dramatic moment. It weakened invisibly over dozens of dives. Bethlehem's engineers understood this intellectually. What they lacked was a proven method to change it. European firms, particularly in Germany, had approached the problem differently. Their forging methods emphasized slow, controlled deformation under immense pressure, refining the grain structure throughout the cross-section. Cooling was managed over extended periods. Inspection focused as much on internal consistency as on surface finish. Bethlehem could not simply copy these methods. Equipment differed. Raw material supply differed. Wartime urgency made slow, experimental iteration dangerous. Yet doing nothing meant accepting continued rejection and delay. By mid-1942, the reality was unavoidable. America did not merely need more steel. It needed a new way of thinking about how steel was forged. Bethlehem Steel stood at a crossroads. It could attempt to scale up existing processes and hope for incremental improvement, or it could dismantle assumptions that had governed American steelmaking for decades. The decision would not be made in a boardroom alone. It would be shaped by engineers, metallurgists, Navy officers, and test results that left no room for optimism without proof. And as these pressures converged, the problem began to fracture into distinct human, technical, and moral dimensions, each demanding its own answer. Human, technological, and naval perspectives asterisk inside Bethlehem's mills. The war transformed routine labor into personal responsibility. Many of the men pouring steel and guiding forgings had sons, brothers, or neighbors already in uniform. They understood, in practical terms, where this steel was going. Submarine hulls did not return for repair when something went wrong. They disappeared. Shifts stretched longer. Training was accelerated. Skilled metallurgists were reassigned from peacetime products to experimental work whose outcome was uncertain. Mistakes were no longer measured in scrap loss alone. A flawed forging could cost a crew their lives months later, in water no one would ever reach. The weight of that knowledge changed behavior on the floor. Workers slowed processes that had once been rushed. Foremen allowed inspections that interrupted production. Arguments broke out over temperatures measured in tens of degrees, over cooling times measured in hours. Speed still mattered, but certainty mattered more. From a metallurgical standpoint, submarine steel lived in a narrow margin between strength and failure. Increase hardness too far, and the steel became brittle. Reduce it too much, and the hull deformed permanently under pressure. Welding introduced heat-affected zones where grain structure changed unpredictably. Forging too aggressively elongated grains. Forging too little left weaknesses untouched. Depth multiplied every error. Bethlehem's engineers realized that traditional tensile tests were inadequate. A sample that survived a single pull to failure revealed little about how a full hull would behave after repeated dives. Fatigue testing became critical, yet it was slow, destructive, and difficult to scale. Every adjustment meant weeks of trials before confidence could even begin to form. The Navy's requirements left no room for compromise. New submarines were expected to dive deeper than earlier classes, to survive near misses from depth charges, and to operate for months without structural degradation. Safety margins were expanded not out of caution, but necessity. Enemy technology was improving. Tactics were evolving. In reports sent back from sea trials, one message repeated: survivability was inseparable from steel quality. Firepower, sensors, and crew training meant little if the hull itself could not endure. These three pressures, human responsibility, technical limitation, and operational demand, did not align easily. Each pulled in a different direction, and together they forced Bethlehem and the Navy toward decisions that could no longer be postponed. Those decisions would soon be shaped by leadership, enemy comparison, and ethical risk, angles that cut even deeper into the problem. Leadership, enemy comparison, and moral risk asterisk. As failures accumulated and deadlines closed in, authority inside Bethlehem Steel began to shift. Traditional management structures, built around production quotas and cost control, gave way to technical decision-making. Metallurgists who once advised from the margins were placed at the center of the process. Navy engineers embedded themselves directly in the mills, not as inspectors alone, but as collaborators. This was not a smooth transition. Executives worried about slowing output. The Navy worried about fielding submarines that might fail under combat conditions. The compromise was radical for its time. Engineers were given the power to halt production if metallurgical criteria were not met, regardless of schedule pressure. In wartime America, stopping a production line was an extraordinary act. Doing so in the name of invisible internal structure rather than visible defects required trust and proof. Intelligence reports and recovered wreckage painted an uncomfortable picture. German U-boat hulls, when examined, showed more uniform grain structures and fewer critical flaws. Their forging practices emphasized deep working of the metal, sometimes at the expense of speed. The steel was not indestructible, but it failed more predictably, giving crews time and margin. Bethlehem could not replicate German methods exactly. Machinery, alloys, and labor practices differed. But the principle was clear. Depth survivability was engineered into the steel long before a submarine ever touched water. This realization reframed the problem from one of quantity to one of process. Innovation carried risk. Every new forging method introduced unknowns. Testing consumed time and material. Submarines already at sea could not benefit from improvements still under evaluation. The question was not whether to innovate, but how aggressively. Some within the Navy argued for conservative acceptance, using steel that met minimum standards to accelerate deployment. Others insisted that partial solutions would lead to long-term losses, measured in sunk boats and lost crews. The debate was never abstract. Names were attached to submarines. Rosters were already filled. By late 1942, the moral weight of decision-making was clear. Delay meant fewer submarines now. Failure meant none later. That tension drove Bethlehem Steel toward a moment where theory, leadership, and necessity would collide inside the forge itself. Reinventing the forge asterisk. The shift did not begin with a single breakthrough. It began with rejection of assumptions that had governed American steelmaking for generations. Bethlehem's engineers concluded that the problem was not alloy composition alone, but how force and heat moved through the metal during forging. Traditional presses shaped steel efficiently, but unevenly. The outer layers experienced intense deformation, while the core lagged behind. In thick submarine hull sections, this imbalance produced internal grain patterns that no amount of surface finishing could correct. The solution demanded something counterintuitive, slower, deeper, more controlled force. Bethlehem reconfigured forging sequences to apply pressure in stages, rotating and reworking each section to ensure deformation penetrated the core. Press cycles were extended. Temperatures were held within narrower bands. Deviations once considered acceptable were eliminated. Cooling, previously treated as a passive step, became an active process with controlled rates designed to prevent residual stress. These changes reduced output, they increased cost, and they consumed time the Navy could not easily spare. Failures still occurred. Entire forgings were scrapped after weeks of work when ultrasonic testing revealed internal anomalies. But patterns emerged. Certain sequences consistently produced cleaner grain flow. Specific cooling curves reduced cracking. Engineers began to predict outcomes rather than react to them. Inspection evolved alongside production. New non-destructive testing methods, though limited by technology of the era, were applied with unprecedented rigor. Test sections were deliberately overstressed to map failure modes. Data replaced intuition. The most significant change, however, was philosophical. Bethlehem stopped treating submarine steel as a variant of existing naval products. It became its own category, governed by its own rules. Forgings were no longer judged solely by meeting specifications, but by how they behaved under simulated operational stress. By late 1942, results began to shift. Rejection rates declined. Test samples endured repeated pressure cycles without catastrophic failure. The steel was not perfect, but it was consistent. And in submarine design, consistency meant trust. Yet steel on paper was one thing. Steel in the ocean was another. The Navy would not declare victory in a laboratory. The next test would come beneath the surface, where theory met depth. Depth tests and validation ***. The first submarines built with Bethlehem's revised pressure hull steel entered sea trials without ceremony. There were no public announcements, no declarations of success. Confidence at this stage was provisional. During shallow dives, instrumentation tracked hull deformation with obsessive precision. Strain gauges measured flex measured in fractions of an inch. Engineers compared readings against predicted behavior, watching for divergence. Early dives revealed what the laboratory had suggested. The hulls flexed, but they returned. No new cracks appeared. No abnormal stresses accumulated. Then the boats went deeper. Each descent was incremental. A pause. Another descent. The ocean closed in, pressure increasing uniformly, relentlessly. At depths approaching design limits, silence inside the hull took on a different quality. Every creak carried meaning. Every reading mattered. The steel held. Subsequent dives pushed beyond earlier safety margins. Not recklessly, but deliberately. The Navy needed to know not only whether the steel survived, but how it failed. If it failed. It did not. The hulls exhibited controlled deformation within acceptable limits, validating months of theory, testing, and costly delay. Acceptance followed quickly. Authorization for mass production of the new forging methods moved through Navy channels with rare speed. Bethlehem Steel was no longer experimenting. It was executing. By 1943, submarine production accelerated. Hull sections forged under the new regime became standard. Shipyards adjusted schedules to accommodate the revised components. Crews trained with confidence that their boats could dive deeper and endure longer than their predecessors. The impact was not dramatic in headlines. No single battle announced the change. But beneath the surface, survivability had shifted. Submarines could evade more effectively. Depth charge attacks lost some of their certainty. Commanders pushed limits that had once been avoided. Steel, shaped under controlled pressure, had quietly altered the balance. And as these submarines entered combat in growing numbers, The consequences of that industrial decision began to ripple outward into production statistics, strategic outcomes, and the long shadow of wartime industry. Production, numbers, and strategic impact, asterisk, asterisk. By the middle of 1943, the effects of Bethlehem Steel's reinvention were no longer confined to factories and test reports. They were visible in fleet rosters, patrol schedules, and the quiet confidence of submarine commanders heading to sea. Production numbers began to stabilize, then rise. Where earlier submarine programs had suffered delays from rejected hull sections and reworked components, the new forging methods reduced uncertainty. Shipyards could plan. Crews could train on hulls that would not be pulled back for last-minute inspection failures. The bottleneck that had once choked output loosened. American submarine construction, already expanding through yard enlargement and workforce growth, now gained reliability. Boats entered service with fewer structural limitations imposed by metallurgy. Design dive depths became operational realities rather than theoretical ceilings. Safety margins increased, not because submarines became invulnerable, but because their behavior under stress became predictable. In the Pacific, this mattered immediately. Japanese anti-submarine warfare improved steadily as the war progressed. Escort vessels deployed depth charges more effectively. Patrol aircraft expanded coverage. Survival increasingly depended on the ability to dive deep, hold depth, and weight. Submarines built with the improved steel could do exactly that. In the Atlantic, where American boats began operating alongside Allied forces, the advantage was subtler, but no less real. The threat environment was already saturated with German experience, but survivability increased options. Commanders could accept greater risk in pursuit of targets, knowing the hull could endure more punishment before failure became likely. Loss rates reflected the change. While submarines remained dangerous postings, structural failures attributable to hull steel defects declined. Incidents that might once have resulted in catastrophic loss became survivable events. Near misses stayed near misses. The Navy took note. Reports credited not only tactics and training, but material reliability. Steel, rarely mentioned in public accounts, entered internal assessments as a decisive factor. Industrial decisions made months earlier were now saving lives far from the factory floor. Yet the story did not end with wartime success. The methods developed under pressure would outlast the conflict, reshaping American metallurgy in ways that extended far beyond diesel submarines and convoy warfare. Those consequences would unfold more slowly after the urgency of combat had passed, when the nation looked back at what wartime necessity had forced it to learn. Industrial legacy, asterisk, asterisk. When the war ended, the urgency that had driven Bethlehem Steel's transformation receded almost overnight. Production lines slowed. Military contracts were renegotiated or canceled. The furnaces that had burned continuously through the war years returned to peacetime rhythms. Yet the knowledge forged under pressure did not disappear. The submarine steel program left behind a new industrial vocabulary. Terms like grain flow optimization, controlled deformation, and fatigue predictability became standard considerations rather than experimental concerns. Metallurgical testing methods refined during the war, particularly those focused on cyclic stress, found applications across heavy industry. Bridges, pressure vessels, and post-war naval construction all benefited from lessons learned beneath wartime deadlines. The Navy carried those lessons forward deliberately. As submarine design evolved toward greater depth capability and endurance, pressure hull metallurgy remained central. The transition to nuclear-powered submarines in the post-war era demanded even higher standards. Although materials and technologies advanced, the philosophical shift endured. Survivability began in the forge, not at sea. Bethlehem Steel's role, however, followed a more complicated arc. Wartime success did not guarantee post-war dominance. Global competition intensified. Industrial practices continued to evolve. By the late 20th century, the company that had once stood at the center of American steelmaking struggled to adapt to economic and technological change. Its wartime achievements became part of history rather than a foundation for perpetual leadership. Still, within naval engineering circles, Bethlehem's wartime reinvention remained a reference point. It demonstrated that industrial limitations were not fixed laws. Under enough pressure, technical, moral, and strategic, processes could be reimagined. Entire industries could pivot. What had begun as a desperate response to an invisible weakness had matured into a lasting contribution, one that reshaped how Americans understood the relationship between material science and military power. And beyond the statistics and legacy, the story left a quieter imprint on how wars are won not only by weapons and commanders, but by those who learn, under pressure, how to make the material world behave. War often celebrates what is visible. Battleships crossing oceans, convoys attacked, submarines slipping silently beneath the waves. But sometimes victory is forged in silence, in places the public rarely sees, inside factories, laboratories, and furnaces where men and machines wrestle with the laws of nature. Bethlehem Steel's reinvention of submarine forging methods was one of these hidden battles. It was not heroic in the cinematic sense. There were no medals, no public parades, no dramatic charges against the enemy. Its heroism was measured in microstructure, in controlled pressure, in the patience to reshape molten metal until it behaved predictably under thousands of pounds per square inch. The human story is no less compelling. Engineers wrestled with unknowns. Workers carried the weight of unseen consequences. Navy officers debated moral risk while crews slept on the promise of steel that could be trusted. Their collective effort turned abstract science into tangible survival. Every successful hull meant not only another submarine in the fleet, but another chance for a crew to return home. Strategically, the implications were profound. Submarines built from these methods could dive deeper, endure more punishment, and operate with confidence. They shifted the calculus of naval warfare. In the Atlantic and Pacific, reliability under pressure saved lives, extended patrols, and allowed commanders to take risks that might otherwise have been fatal. Ultimately, the story reminds us that warfare is not only fought on front lines. Sometimes it is fought where the heat is controlled, the hammer strikes measured, and the material world is bent to human ingenuity. Steel, shaped under pressure, became more than a hull. It became a silent weapon, a safeguard, and a testament to the quiet power of innovation. In that sense, the lesson of 1942 is enduring. In war, as in life, it is often the invisible, painstakingly perfected elements that determine who survives, who wins, and who is remembered.